The order of an algorithm represents the amount of time and memory required in relation to the size of the problem it's meant to solve. It can usually be determined by the number of steps needed to complete the algorithm. We normally use either or both of two metrics to define it: time complexity, this being the most common of the two, and space complexity. The time complexity of an algorithm represents how changes in the size of a problem affect the approximate runtime of that algorithm. The space complexity of an algorithm represents the amount of computational memory required, in addition to that used by the dataset, to solve a problem as it scales. Big O notation is simply a means by which we can express the order of an algorithm mathematically. To the right we have a set of common orders of algorithms and their corresponding Big O notations. The order of an algorithm can be described as a function of its size. If an algorithm has order f of n, then increasing the size of the problem from a to b will increase the runtime of the algorithm by an approximate factor of f of b over f of a. It's important to note that Big O notation only refers to the highest order term in a function. This is because the highest order term will grow faster than all of the other terms, meaning as n becomes large, the other terms will become insignificant. To demonstrate this, let's take a function with order 3n squared plus 5n plus 9. Here, 3n squared is our highest order term. Now let's see what happens if we set n to be equal to 1. Our highest order term will take on a value of 3, whereas our two lower order terms will take on values of 5 and 9 respectively. Now, as n scales up to become large, say n equals 100, we'll see that our highest order term massively outgrows the other two, taking on a value of 30,000 compared to 500 and 9 respectively. As n increases further, this gap will only serve to increase. Hence, as n grows, the other two terms become insignificant, and it's only our highest order term that we need to base our order on. By plotting the orders of algorithms as their mathematical functions, we can see how resource efficient each of the algorithms are for varying values of n. The graphed order that emerges above the other one from an intersection is the most resource intensive of the two. This shows us that the exponential and polynomial orders are the worst, followed by the logarithmic and linear orders, with the logarithmic and constant orders being the least resource intensive. Linear search has a best case time complexity of O of 1. This would occur if the item is at the start of the list, in which case it will always be found in the first step. It has a worst case time complexity of O of n, because the time taken is directly proportional to the index of the target, which means it cannot exceed n. For example, if the last item in a list of length 10 is the target, then 10 comparisons are needed. Binary search has a best case time complexity of O of 1. This occurs when the target is at the midpoint of the list and so is found straight away. It has a worst case time complexity of O of log n, as the list is split in half after each comparison. We derive the logarithmic time complexity by thinking of the goal of a binary search as being to halve the list until there is only one item left. So n becomes n over 2, which becomes n over 4, which becomes n over 8, until just one item is left in the list. At this point we know if the item is found or just not in the list. So if we call the number of halvings to get down to only one item being left in the list, k, then we can say that n over 2 to the k equals 1. Timesing both sides by 2 to the k, we get n equals 2 to the k. Now taking log base 2 of both sides, we get k equals log 2 of n, which is our time complexity for the binary search. Here's a question you might come across while studying the orders of algorithms. Pause the video and have a go now if you'd like. The bubble sort algorithm has quadratic order. If it takes a computer 0.5 seconds to sort a list of 2,100 numbers using a bubble sort, estimate how long it will take to sort a list of 840,000 numbers. To solve this problem, we must first recall that increasing the size of a problem from A to B gives us a scale factor of f of b over f of a when the algorithm has an order f of n. So, applying that to this question, since bubble sort has a quadratic order, we can calculate the scale factor by working out 840,000 squared over 2,100 squared, which gives us a scale factor of 160,000. Now multiplying this by our original time taken of 0.5, then we will get a time of 80,000 seconds. Now for a summary of the key points. The order of an algorithm is a measure of the efficiency as a function of the size. An algorithm can and often does have separate orders representing its time and space complexity. The complexities in ascending order of relative performance are constant, logarithmic, linear, linearithmic, polynomial, and exponential. Lower order terms and constants are ignored in big O because they become irrelevant for huge datasets. Please leave a like and subscribe and tune in for the next video.